All right, so let's continue our discussion of the initial rates method. Last time we said that what we do in the initial rates method is we run a series of experiments, at least two, okay? And for all these runs, we maintain the concentration, the initial concentration of all the reactants except for the one we're interested in, right? So, for example, if you look at this pair of experiments right here, experiment 1 and 2, you triple the initial concentration of B, you kept the initial concentration of A the same, and so what will these two experiments tell us? How concentration of B affects the reaction rate. And so if we measure the reaction rate for both of these experiments, suppose we find it to be 0.05 in both cases, then we figured that it's not affected by the concentration of B, so we say the reaction is zero order with respect to B. Okay? And if you compare experiments 1 and 3 then, okay, you can see that, I'm sorry, 2 and 3, actually it doesn't matter anymore. Now that we've established that B doesn't matter, right? If you compare 2 and 3 or 1 and 3, what happens? By doubling the concentration of A, what happens to the rate? From 0.05, it becomes 0.1. So that also doubles, right? So we say that the rate is directly proportional to the concentration of A. So we say that it is first order with respect to A. So that allows you to determine the order of the reaction. Okay, so one last step in determining the rate law is to determine what the value of this K is, this rate constant. So what do you do with that rate constant? How do you figure that rate constant? All you have to do is go back to your data and plug in the numbers. So your initial rate, by the way, these are initial values, okay? So this is initial rate, that's initial concentration of A and B. So you plug in the initial rate for, let's say for experiment 1, you put in 0.05 moles per liter per second, that's your rate, is equal to K times the concentration of A for experiment 1 is how much? 0.1, right? So raised to the power 1. And the concentration of B for experiment 1 is 0.1, and that's raised to the power 0. So you can solve for K. How do we solve for K here? We say K is equal to 0.050 divided by, okay, that's moles per liter per second, divided by 0.10 molarity, moles per liter, times, what's something raised to the power 0? It's just 1, right? It doesn't depend on B. So this gives us how much? 0.05 divided by 0.1. It's going to be 0.5, right? 0.50. What happens to your moles per liter? Cancels out, right? So the unit here is just per second. You can see if the overall order is per second, you remember? The overall order is just per second. 1 plus 0, 1 plus 0 is 1, okay? Then the unit for your rate constant is just per unit time, per second or per minute, depending on what you're doing. And you can do the same for experiment 2 and for experiment 3, and you should get essentially the same number. Now, if you're dealing with real experimental data, though the K values you're going to get for each run is not going to be exactly the same, right? Because of random errors in your experiments. Okay, experiments are always subject to random errors. You don't always expect to get the same thing. So what you can do is you can plug in the numbers from experiment 1, experiment 2, experiment 3, and then take the average. Okay, that would give you your rate constant.